It's wonderful to meet all of you. Erin had shared the invite list ahead, so it was clear that we have a really broad-ranging group of folks that are here today. And so I don't know whether to stand or sit, what'll make you more comfortable in all of this. But the thought is to frame a possible conversation. So I'm going to look at, why improve, what we know about improving and where we might go, but in a, at a fairly broad level so that we can spend time in discussion. So there's about 20 slides, there's discussion, and then there's I packed a lot of other slides behind that if there are specific things you want to go into, conversations you want to have, because I would really like to make this a session that's valuable and relevant to what your interests are at this point. So just to give you a little sense, my permanent home is at Carleton College in Minnesota. This is my second time at NSF. I was there in the biodirectorate when the Arabidopsis genome was getting sequenced and we were working on the rice genome. And this time I direct the Division of Undergraduate Education. And so we're working really hard on a strategy to catalyze improvement in STEM fields, which include the social sciences. That's one of the areas we fund at the National Science Foundation across the nation. So why would we want to improve undergrad ed in general? And there's lots of reasons, but this is just such a compelling graphic that came out in the last few months comparing here we're 1965 to today, looking at bachelor degree attainment as a function of your socioeconomic status. So back here in 1965, 6% of students from low-income families achieved bachelor's degrees, and about 40% from the upper middle class. But now we've got a 9% versus a 77% difference, and we've gone from ranking first in the world in terms of college degree attainment to 12th if we look at young people, right? So it depends on which age group. And then, so what are the challenges? Why is this happening? Can we begin to break some of this down? And again, this is not perhaps the most beautiful way to present data, but it's how Carnevale and Stroll chose to do it. What I want you to keep in mind here is this is data for students entering college that are in the top quartile, right, based on SAT and SAT-like tests that are adjusted. So these are students that are talented based on common metrics we share. And again, each cluster is looking at breakdown by students coming from high SES families, low SES. So you've got twice as good a chance of just attending a four-year college if you're in the upper quartile than the lower quartile. And what I find really compelling, only 6% of all students in that quartile that are from high income don't go to college. 31% of low income don't. And certainly SES is a proxy in some ways for other things, but not completely. So there are a lot of other factors. This also came out in February from the Washington Center of Equitable Growth and Economic Perspective. I think you can go in and look at this analysis and the extrapolation and be critical as one can of any of these type of things. But the overall message, I think, whether the exact conclusion is spot on or not, is worth considering. So if we were able, in the science and math scores on the OECD scale, to move just up to where Canada is in this country. So we have, in some states, like in my home state, our OECD scores are, right up there competitive with the rest of the world. In some other states, they're not. Massachusetts hits the top. So it's uneven, but this is looking at the US in aggregate. The claim being made, trying to find some way to get people to realize that education as a whole matters, is that there would be a 6.7% increase in the gross domestic product. And if you took into inflation and made some other estimates, by 2050, you could increase our GDP by 10 trillion. Again, I think the numbers, one could argue, but it's an interesting thing to think about in terms of why we should care about the success of everybody, not just the kids in our town or our school or our house. There's also been a lot of noise about we need more STEM workers. And I would like to not go in the direction of we need more X or Y or Z, because those predictions often end up being faulty. You know, when I was in undergrad, you know, my chemical I was in materials engineering, but my chemical engineering friends, you know, one year everybody's getting great $60,000 a year job, the next year nobody was getting a job. It's really tough to make large-scale predictions, but focusing on quality matters. But part of the argument you hear is that, oh my goodness, science faculty are horrible, their students leave. And I think we're not different than what we're seeing in other non-STEM fields. So this is out of the National Center for Education Statistics. This figure is very difficult to see. This table over here is my synopsis of it, so we're going to go here. When you put something up, people are going to look at it anyhow. But the dark blue bands are students that come intending this bachelor's degree, starting out with a bachelor's degree, intending to major in STEM or non-STEM, and then starting in a community college here and intending to major in STEM or non-STEM. Dark blue, they leave college without any degree. Light blue, they switch to another field. So these numbers here are the combined switch or leave STEM, not really different than non-STEM fields. And then with the associate's degrees, not different. But that's a pretty appalling number if you start to think about people leaving as well. And the question I think that is important to ask is who's leaving and why? My daughter left math to do French Lit. Well, I think that's pretty awesome, right? I'm really proud of her. But there's lots of students that leave because they really, really wanted to be a mechanical engineer, really wanted to be a geoscientist, and they couldn't get past something, which often the something is mathematics. So again, nationally, 60% of our students are arriving not ready for college-level math. And students that start out in developmental math, this is really depressing. 5% successfully complete developmental math. Now, there's some other strategies we can talk about later that have been very successful and have tripled the success in half the time. But of those students who don't complete developmental math, 80% of them are going to leave without any college credit. So does this just matter for science and engineering? Probably not. Again, think about so many of the social science courses where there's a lot of concern about not, having enough statistics to even be successful in the major. And then we talked about SES, so I wanted to bring in just in one way different demographics. So if you do race and ethnicity and you look, for example, the percent of students that are going to take advantage of special tutoring, remedial mathematics during college, again, it's disproportionate across different ethnic groups. If we're looking at a country, which we are, that by 2040 is going to be a majority-minority country, and we want to build capacity across disciplines, if we're leaving out huge chunks of the population, we've got a serious problem to consider. So next I want to step back and talk about, at a more national level, what's been driving some of this change, and more of it has come in the direction of STEM fields for many different reasons. But 2012, besides being the year of the MOOC, was a very interesting year in a number of ways. It's when the President's Council of Advisors on Science and Technology rolled out their Engage to Excel report and made a number of key recommendations, 3 of which I think are particularly salient to where I'm trying to shape our conversation. One is to get evidence-based practices out there. The other is to think differently about how we do the laboratory learning part of undergrad education, and then to begin to address the serious math problem. This got the math community, it troubled them that this particular remark came out, but what is very interesting is in the last 3 years, the change that has occurred in the math community writ large in terms of undergrad ed is phenomenal. There's a new journal that's being launched specifically focused on research in undergraduate mathematics education. So it's stirred up a lot. Now, it wasn't a coincidence at the same time, this report, and I chaired the study at the academies on discipline-based education research, which is a synthesis of what we knew as of 2012 across science and engineering disciplines about learning and understanding at the undergrad level. It was the first time we synthesized across disciplinary boundaries. So this was kind of the roadmap for, if you're going to do this, what does it look like? What's the evidence? What do we actually know? Math was not included in here because at that point, there were a lot of distinctions. Also, the level of, the number of research publications wasn't there in the same quantity that we see elsewhere, and that's really changing rapidly. So then by 2013, across the federal agencies, we rolled out a strategic plan to improve STEM education. Now, because we're talking about undergrad ed, I've honed in just on the undergrad strategic objectives. And one of the fascinating things about the time I've been in Washington is I get to convene the group of 14 federal agencies where we're trying to figure out how to implement the strategic plan, how to develop shared metrics. You can actually check our progress on performance.gov because we have to do quarterly reporting. But you'll begin to see, and I think this is interesting from a policy perspective, how things grow. These are our 4 strategic objectives, and they probably won't surprise you after you just saw the Engage to Excel report. So implementing evidence-based instructional practices and innovation, pushing hard on the challenges in community colleges and the transfer challenges, and pushing on authentic research experiences, addressing the high failure rate in mathematics. So the notion here, and then also we've been working across the foundation at NSF in exactly the same way, is how do we all take what levers we have, right? And in the case of the federal government, it's things like grant making, professional, the ability to convene groups, to provide technical assistance. What can we do with our set of levers to, in a much more coherent way, push to catalyze change? So some people say, you know, people keep talking about evidence-based practices. Why is everybody jumping on the evidence-based practice bandwagon? Where did that come from? So and this largely influenced the PCAST Engage to Excel report. 1997, Elaine Seymour, beautiful ethnographic study at a whole range of institutions carefully selected from, you know, an Ivy League school to liberal arts schools, going in and comprehensive, understanding why students were leaving STEM fields. And across all demographics, one of the top reasons was the quality of the teaching. The response to the quality of the teaching varied, right? So many students were underrepresented groups. Women left because the teaching was bad, but they felt they couldn't learn, and they took the responsibility. Many majority students also cited poor teaching and put the blame on the faculty, but the theme was consistent. Then by the time we actually synthesized the literature about evidence-based practices, the data that's out there shows that bringing in effective practice where you engage students in their own learning does increase the learning gains of those students and their persistence and success. And then very interestingly, some of you may have seen this past summer, and I think Scott Freeman may have been here also, the Proceedings of the National Academy of Science paper where Scott and his team did a meta-analysis of papers on active learning, so as students engage in their own learning, and what impact that had on whether they failed or persisted. So it's a persistence, not the quality of the learning, but do you persist? And this was driven by the conclusion of the PCAST report where the claim was made that if you want it to get to 1 million more STEM workers, right, and that was just the framing of that particular report, by having evidence-based practices in classrooms, you could get 75% of the way there. So Freeman's analysis extends to that. You can push back on the analysis whether the conclusion goes a bit too far or not. But what is interesting is when you look at these papers, and many of them have been funded through the NSF, and density is just the a indicator of the number of papers. The blue are papers where active learning strategies were used, and the orange or tan is where more traditional lecture base was used. And the curves shift in terms of the percent of students who fail. So, and this has gotten a lot of traction in the community. It was presented in a way that was accessible to people, and so kind of why there's a lot of interest in integrating evidence-based practices. The other is, why authentic research experiences? So NSF has been funding REUs, research experience for undergrads, since 1958. I went back and I read the history, 1954, 1956, all these convenience conversations, and the belief that faculty that are engaged in research are more effective teachers, right? So getting the research going was really important in that context, and I think that points out how things cut both ways, right? But there's a real scaling challenge with that. And this was a study I shared at the academies back almost a decade ago, looking about what we know about lab learning. Most of it came from high schools, and the importance of it being conceptual, tied into learning. This is spilled as more research has come into what we know about the framework for K-12 science education, and now the next generation science standards. But a traditional lab isn't quite all the way there. The PCAST report says that. REUs, there's a limit to the number of faculty, the amount of lab space, what you can do. So there's been a huge sea change in terms of course-based research, bringing your own research into the classroom, or collectively doing research amongst many different institutions, but where the students are really generating and analyzing legitimate data. If you look at our budget request for 2016, you'll see that's a priority. For NSF, we're seeing an increasing number of really terrific ideas. We have research coordination networks we fund where people are working on this. Next week, there's a convocation on this topic at the NRC, and we're funding a consensus study that'll help us know what we really know, because it's a little bit like research experiences. We have a lot of self-report data from students, which is informative and helpful, but we don't know as much about the student learning as we could. And this may be a really good way into learning about how students learn in the laboratory, doing the practices of science. And there's all kinds of models. These are two from my own work. One was a consortium of liberal arts colleges that worked to help faculty bring their own research into the genomics era and get it into labs, so it built on their expertise, which is different than some models where someone out there has a terrific project and they get everybody else to help with their project. And then we have pushed further, trying to figure out with in genomics, right, there's tons of data out there. So we generated sequence data for our students to do authentic research, but thinking at the scale of big data is really tough for biologists who default to hunting and pecking for their favorite gene. So thinking about how to scaffold that and what we could use in a web-based environment, and then what all the challenges are with learning from a whole mixed methods approach there. But just examples to show that there really is active research going on in this area and that it's moving pretty quickly. So how do we actually, if we agree that it's important to improve education as a whole, and we agree that it'd be good to do this in the sciences, how do we begin to leverage this opportunity? And what fits with my thinking, is clearly reflected by all of you around the table, is that we need to partner more, that there's so much siloing, that if we could knit things together, we could all move together forward at a much faster and more effective clip. So I like this was a graphic EDUCAUSE did for a paper I had last month, but just to push on the partnering idea. And given the exciting conversations I've had with all of you today about HILT and Harvard X, really thinking about the two huge changes that are going on right now. Lots of advances, and I'm using learning science as a general way to encompass ed psych, cognitive science, cognitive psychology, social psychology, the whole gamut. So allow me to use it as a grouping word, and recognizing that there is a learning science society that is trying to move cognitive science out into the world. And there's an incredible opportunity to improve online learning by integrating what we know about learning science, and then iteratively to do research that was not possible before because of the scale of the online environments. So I think there early on, right, 2012, there was a lot of concern about, oh my gosh, what's going to happen to universities, what's going to happen to faculty. I think we're asking the wrong question if we go down that route. I think we also ask the wrong question if we're like, is online better than face-to-face, right? That we want to get past that point. And what I would hope people do is say, wow, what can we do right now with all the pieces that are out there that we've never been able to do? How can we take all the opportunities that are out there and change the way students learn? So just to give you a sense of this partnering, and I'm just very briefly going to pull from some, but not all of the possible partners, because again, my concern about things being siloed is just to make a plea for more conversation, because we can all learn from each other. So you've got this whole notion of developing expertise, and we know from chess players and others about what it means to develop expertise, but I think that's one of the key things we're trying to do in the undergrad years, right? That you come from high school, you're beginning to focus on a major, and when you leave, no, you are not going to be a full expert, but gosh, unless we've moved you along that expertise continuum, we failed. And we know a lot about productive practice and trying to get the right level of jump and challenge. If you ask someone, to once again solve the same math problem over and over, they're not going to move forward. But if you take someone that has had algebra and you suddenly ask them to do partial differential equations, it's too big a jump to make. And figuring out how to scaffold things, it's some of our research on students learning in genomics ended up the stumbling block in our network was figuring out the right level of challenge. It seemed great to us and the students just froze, or the students were just zipping through, but there were no gains in terms of critical thinking because we hadn't challenged them enough. Things like retrieval practice, right? The testing effect, really building on this notion of formative assessment. Lots of great findings within cognitive psychology. And then the cognitive psychologists and educational psychologists coming together in a partnership that I thought was beautiful. Dunlosky and colleagues in Psychological Sciences for the Public produced a very nice paper where they looked at meta-analyses and syntheses of all kinds of things about learning from cognitive psych and said, well, based on the range of things they cover in the evidence, what would we recommend? And so this was really a high priority there. For things like interleaving versus cramming for your exam, it seems very likely that would work. That was an intermediate priority, and so a really rich area for us to all dig in more. And things like elaboration, so talking about your understanding of a concept and creating your own mental model helps with short-term memory constraints and more lasting learning. In some of the science disciplines still, there seems to be this urge to go and think about learning styles and whether you're an auditory learner or a visual learner, and the results are at best equivocal there. There's also one of the things I'm very excited about is how we're beginning to see a move from some of the findings in social psychology and related fields into thinking about learning. So I would agree non-cognitive is a horrible labeler for these terms. So I tried to elaborate them a bit. Things like collaboration, communication, how do you learn to learn? You know, what's your mindset? Oh, I can learn math if I work hard versus I'm not good at math, or I'm a rock star at math. And you know, even believing you're a rock star at math, if you start at middle school, by the time you get to the end of high school, you're not a rock star anymore. But if you can adjust your mindset, and these are all malleable, right? So thinking about malleable traits versus things that just say, we're going to set you on the shelf over here because you know you're just not going to make it. Resilience, motivation, your STEM identity in general, social capital, so things like Claude Steele's work with stereotype, threat, things like the way we use language, microaggressions, really interesting to think as you work across diverse groups, what those roles are, and some very interesting things playing out in online environments for testing, interventions that ameliorate some of these challenges. And then, you know, as Aaron said, you know, where does the discipline fit into this, and the importance of, especially in the undergraduate years, but I don't think this is limited to the undergraduate years, where does the discipline fit in helping to advance things? And one of the areas, this is an assumption I walk around with, I think many people do, and we actually have not really asked the hard research questions. If you bring frontier science and cutting edge education research together to create robust learning environments, that just seems like a really good idea, right? And at the NSF, we're the only federal agency that has a dual mission in education and research. And when we write budget language, when I look at our strategic plan, we believe this. We could do a lot more to figure out what's the relative importance of that and why. Is it the enthusiasm of the instructor, the engagement? Does it excite students? Or in the case of bio, the huge shift, there's been a transformation effort called Vision and Change in undergrad biology that really has had huge national impact, but it was driven by the fact that we were teaching biology as a descriptive science, and it's a data-driven science. So we were teaching students in, circa, some place in the 1990s or earlier, and then they're going out to grad school or going to work and being asked to do something that has, looks very different than what they experienced. So the field got very motivated to change. What I think is really interesting for those of you that have more of an education background in a historical sense, this idea of deep disciplinary knowledge and education research meeting, it should be deja vu. The whole point of science education research that started in the US in the late 60s into the 70s, Bob Karplus at Berkeley and other places, was that education wasn't disciplinarily agnostic. And this was a huge conceptual upset. And most of us in higher ed are just kind of rediscovering this, and we're kind of missing the point that it already occurred, which I find fascinating. But nonetheless, the important thing is that we're looking at how it is. So you've got this field called discipline-based education research. So deeper scholars also are siloed. So the physics education researchers, they don't always talk to the biology education researchers. So we've got that going. And some of them just haven't ever dug into the social psychology literature, the cognitive science literature. It's all news to them. So we're all saving the world in our own little world and reinventing or scaling things that actually aren't effective. So I wanted to just give you one example. So this paper that just came out this week, it's an investment that we made at NSF. We've been very excited about that occurred in Chicago, and psychologist Sian Bialik and then Susan Fisher, physics faculty member, and then the graduate students that worked on this were interested in embodied cognition. So how much, our brain's involved in learning, but what about the rest of our body? So I figured we needed one example. So what Sian and Susan did was in introductory physics, the concept of angular momentum, and all your physics colleagues can help you out with this after, is a really tough one to understand. But you can experience it if, as this student here is doing these spinning wheels that she's holding on to, you're building up this torque. And then if you turn the wheel, you physically feel that in your body. So they set up an experiment with their intro physics students in lab where some folks got to get knocked off their feet. I would have probably tipped over with the wheel, and other students watched. And so it was a demonstration versus experiential. And then they had them solve physics problems, including the embodied cognition, the angular momentum questions, and no difference on the non-angular momentum questions, but huge difference with the angular momentum. If you experienced it, you got it. So then, and this, I'm thinking, David, this suggests that they're not there yet, but down the road, neuroscience is going to help us so much, right? So the hammer that's being used right now is functional MRI. So oxygenated blood lights up differently than non-oxygenated blood. So they got these students, and I guess they all signed consent forms. I would have just freaked out, not been able to do this as a student, but they all went in, the subject went into fMRIs where you can't move, right? They're the tubes if you've been in one, but you can, do your fingers. So now we have students in fMRI tubes answering physics problems, moving their fingers. They're no longer experiencing the angular momentum. There's been a weeks delay, more than weeks delay in this. And the students that felt the angular momentum still do better on the problems. And interesting, very different parts of their brain light up. So what does that mean, right? And what does that mean for how we learn? Well, it just unleashed, in my mind, a whole bunch more questions. But I think it's a really nice example of taking a whole set of research tools and approaches, bring it to bear on a real world problem, learning something different, and then beginning to ask questions, not as something better face-to-face or in classroom, but when are there learning opportunities where what's looking promising in terms of embodied cognition, we really need to focus time on that in the physical world. And what are the things where there is real value to doing this in an online environment, and how do we begin to make good decisions about what to do? So the importance of a research agenda. I want to step back and say that, in terms of what we actually know about undergrad learning environments, and if anybody's interested, we can unpack this more in the conversation. We know a lot about students' conceptual understandings or their misconceptions. We know how to fix it a little bit. Phil Sadler has just done beautiful work here, right? I like the photosynthesis one as a plant biologist where you give someone a big tree, Harvard students graduating, to be fair. And where did the mass come? Beg pardon? Well, so my plant biology colleague at Carleton is an MIT grad. We choose the video, and she's so funny. She actually says, no, they're all Harvard students. So I don't know. I'm sure it was the engineers.
I was there, but never.
Really? So I can go give Raka a hard time that she's being an MIT snob. I will. Anyhow, it happens to everybody. It actually doesn't matter where you go, right? The idea, but it's just so beautifully done. The idea is that the mass of a log, to just tell the whole story so we aren't leaving people out in the dark, right? Carbon dioxide as well as the contribution from water adds to it. And students, although we've done it from middle school on, we've spent millions of dollars improving, just don't get it. So understanding why they didn't get it was really important. The reason they don't understand is it's really hard to believe that air has any mass. But now think how cool dry ice is, right? Which is solid CO2. So now you get to play with dry ice. You watch it sublimate, right? Go from the solid to the gaseous phase. And that's enough to help you believe that carbon dioxide could have mass. So now an intervention comes out of this really nice bit of research on understanding it. And all of a sudden, we have a lasting, enduring understanding of a difficult concept. But we don't have as much research on how to do the conceptual change as we do on what students don't No. And that's a start, but it's not an endpoint. Lots about problem solving, lots about how to effectively use representation, some great stories there. And we know a lot about effective instructional strategies, right? Since the early 70s, when this active learning came out before cog psychology was named cog psychology, we've known that if you're engaged in your learning, you do better. We now have thousands of studies across disciplines that conclude exactly that. It's time to move on to the next phase to understand a bit more. But there's a lot we can build on, and we ought to be building on right now. And then I just, given all the Harvard X work and all, wanted to point out that I think the MOOC research, but I think also all the work you're doing at HILT knit together can help fill in some really huge gaps. So these are the gaps we know about in STEM. I've been working with the Social Science Research Center in Brooklyn, where they've been working on learning outcomes across a number of disciplines, economics, business, as well as biology. And there isn't as much data about where the gaps are there. They're broader gaps because the literature base isn't as deep, but likely there's similar gaps and we could learn from that. At the undergrad level, we've not been good at disaggregating different demographic groups. We have some, these scale-up classrooms, interactive classrooms, quite promising. And we also don't have much in the way of longitudinal studies. The average DBER study is 18 months long. I just found that maybe not surprising, but we could do better. The basic research piece, how do we knit together, and that was the point of the earlier slide, how do we knit together some of these pieces to bring what we know about learning into this and to test and see how much the context matters, but do it in disciplinary context so we're studying something that's of value to the discipline and not working really hard on something that sounds interesting but isn't core to understanding a discipline. How do we translate the findings into the class, right? So that's my understanding what your seminar's about and all. This is actually something people are working very hard on. It's a major portion of our funding effort at NSF also. We've all got a long way to go. And then I just wanted to add, we've got a long way with the whole affective domain, interpersonal, the intrapersonal studies. We've two interesting things we've funded. The NRC is doing a study on how do we actually measure, what metrics are out there that we could use to assess the traits that are most relevant to persistence in completing a college degree. And many of these actually are also tied directly to satisfaction with your employment long term and to your health, your physical well-being. So this is about much more than whether if you wanted to be a chemical engineer, you get to be a chemical engineer instead of having to go become a civil engineer or something else. I think it's much more significant than that. And as you're all in the thick of this, reimagining research in this world where we can rapidly iterate and learn to improve. And there's lots of things we can do with A/B experiments. I think what we have to keep in mind is right now, because it's so new, there's a lot of low-hanging fruit. But my view is we need to step back and think about what are the bigger questions, where do we really want to get, and how do we build the research methodology in these new environments at the same time we're building the environments so we can keep learning and moving forward and not just being happy with what we can do today, because next year we're going to have new challenges. There is two different resources in the federal government. There's common guidelines that the Institute for Educational Sciences at the Department of Ed and we at NSF jointly developed to talk about what education research looks like in a more accessible language. I think it's very helpful. We find our grantees find it very helpful too in thinking about how you talk about your research. And another document about expanding evidence approaches for learning in the digital world, which really pushes hard about how do we think about methodology now that we have a different playground. Again, this reflects my genomics background and history, but I think we've got a couple things going here, right? So we're generating all this data. So we now have data-driven research. We're seeing patterns. We're learning from it. But one of the challenges in educational research has been to develop theory, right? We're not the most robust, sophisticated theorists. Biology, understanding evolution has made a huge difference to us. But one drives the other, right? They're related. And the lesson learned for me from, biology is we went through a period where we spent a long time figuring out how to sequence every little base pair, every A, C, T, and G. It was the ultimate reductionist experiment for biologists, not for the physicists in the crowd. I know you go much smaller and deeper than that. But for those of us biologists, it was. And people were really frustrated and just saying, this is, well, that's great, but we want to think, we want to ask questions. And the reality is now that the field is so much better for it because the data is driving the theory is driving the data, it all fits together. The takeaway from this, though, is it took us about 20 years, and I'm not sure that in the interim we did the best job we could with continuing to educate our undergrads and our graduates in terms of the theory, the big picture, biology, how to do question-driven science. So in education research, let's learn from that and be able to do both the data-driven research and the question-driven, theory-driven together. Yeah?
Rather than theory-driven research, why don't you say question-driven research?
I guess because I'm a biologist. Question-driven research is a really...
Questions pervade biology.
They do.
I'm not a biologist, but I can list lots of questions that are fundamental.
They're all question-driven. So I absolutely agree. I would also say one of the conversations, and our education research colleagues can speak to this too, which I think would be very interesting. Education has certainly been question-driven, but in education we don't have as many coherent theories about what we think is working and why, and we don't have the conceptual framing that might allow us to advance together. So let's come back to that, because I think that would be a very interesting conversation about questions, data, and theory-driven and theory-building work.
Susan, it's about 3 o'clock.
Oh my goodness. Yeah. Okay, we did take a little time to introduce,
yeah,
right? But
did.
Let's stop so we can have, so this is actually the last slide. It was to say that we have been funding a lot of work on transforming institutions, and we can talk about that, but the key pieces we've been finding is that when there's a theory of change or a theory of action that's driving the whole effort, people move further. And when you have both top-down and bottom-up engagement, you get further. And when you remember to start with baseline data, we have been repeatedly surprised that people talk about improvement, but they don't know where they started from. So lots of opportunities and challenges ahead. We really need to think about how we get the research and implementation infrastructure. And as we start learning anytime, anywhere, I think our biggest challenge is we're going to a disaggregated model of education. How do we get out in front of that? And it may be by just helping students learn and articulate their learning, but how do we help people make sense, drive coherency in their learning? Okay, so yes, now we should have conversations. So I will sit down, and I'm very interested to hear what you're thinking about. And you should talk to each other as well as talk to me.
In the first part of your talk, you were mostly focused on people trying to penetrate the first barrier to low-level college learning and the real obstacles that people from less privileged backgrounds have in entering into the conversation. Right. There's another kind of problem which we face here teaching our students, which is oftentimes students are very good at something that's not science. I mean, certainly that's an experience that we've all had here. And also the heterogeneity of our students. We have, sophomores that are doing string theory and sophomores that are afraid of 1 divided by a half. So and they're often in the same room. And then there's the experience that a number of us have with distance learning, trying to figure out how to calibrate an audience that we only very partially understand in terms of what their backgrounds are. And we know statistics on who stays with the course and so on, but we don't really know the details of their backgrounds so much. And we know from their age distribution roughly where the peak is, and it's got a long tail towards older years, and it cuts back into high school somewhat. So, they think I couldn't tell from the last part of your talk, or the last 2/3 of your talk, whether you were continuing in the comments in your concern about penetrating the first barrier to being in any, and getting an associate degree and leaving the field because you hadn't mastered a quadratic equation or whatever, or simple one variable equations or something. So I guess my question is, do you think about these other learning strategies, which were at a more abstract level, as addressing primarily entry-level work into any technical field, or do you think of them as equally about trying to teach this more heterogeneous audience of, up through advanced undergraduate and education in science?
So yes, to the latter. And the student population at Carleton, you're sitting next to one of them, is not dissimilar. I have many conversations about students that are deciding whether they're going to go to Harvard or Carleton. They usually go to Harvard if it makes you feel better. But a very talented student population, right? But also often very passionate about other disciplines, curious about everything, very hard to figure out what you want to do. But I think these approaches apply throughout the undergrad years. I think they apply to K-12. When you get to graduate school and beyond, I think we know less, and I think we may find out that it's different, because once you develop expertise in the field, you can learn in a very different way. I mean, would you want to go to a professional society meeting where everything was done with, talk to your neighbor now, long discussions, right? Because and I think this is part of the reason that we're seeing some online work where advanced degrees, master's degrees, are really amenable to that, because we don't have to deal as much with getting someone from novice to expert status. So novices look at the world differently. They pay attention to superficial details. You give them problems at the back of a physics chapter, and they group all the inclined plane problems together because they look alike. And you give them to a physicist, and they might group them based around conservation of momentum, because that makes much more sense in terms of the field. So that, and we also, there's just so many things that are different, right? The way people solve problems. A novice might start working backwards, trying to hold the units in their head and trying to figure out what things they could put together that would get the units at the end. So I think a lot of this push is most appropriate through the undergrad years. And as you become more expert, I think you need less supports in your learning. Does that help?
I guess what I have in mind is an audience of students that are used to conceptual thinking, but are fearful of science, as if it has nothing. Yes. A lot of my experience here has been with students who, if you ask them to compare the early and late Weber, they're great. So conceptual development is not their problem.
Right.
And command of syntax, vocabulary, even visual acuity about analyzing things in the pictorial world is all familiar to them. Right. But they feel like when the decoder badge for science was handed out, they were absent.
Right.
And they don't, so a lot of the effort that I think a lot of my colleagues put into it is convincing these students that they have the skills to think about ideas, and that physics, in my case, or some of my colleagues here, are about ideas, which is a new idea for them, actually. They think it's a special it's like a secret language that they don't know, and that they're not equipped to know. And so just the idea that there are actually ideas in physics, that conservation of mass is not a secret
It's
signal
not a
ring.
fact
It's
that
actually
you
an
have to-
idea like an idea from literature.
Right.
That I think, but that's different for students that come from such a radically difficult prior background, that they haven't had the experience of working with the consistent development of a set of concepts in any field.
Correct.
So you're really bringing them into a culture of concentrated study and reading and learning habits and all sorts of things that are not actually it seems to me a different problem.
So you're bumping up against two things, right? One is a belief system. So the whole affective domain and mindset and everything is a key point that sounds like you're working on. The other piece is, I could be really good at biology, but if you moved me into, an art history domain, I'm a darn good conceptual thinker, but I would have to work deliberately to develop my expertise in art history, because expertise is domain specific. And I think we have to acknowledge that as well, that this whole set of skills are very useful, and they're a way in and they're a way to get students thinking, but there are other parts of, and not just the vocabulary, right, with learning a language, but there are other parts of the ways of thinking. There, being a conceptual thinker and being able to unpack, say, a phase change diagram. We talked about going from solid to gaseous CO2. We actually do have secrets in all our disciplines, and most of those secrets are locked up in the visual domain. We have shorthand for how we present concepts. It's a secret handshake, and we have to help people unpack that. So yes, it's a representation, and yes, you're really good at representation, and you can do this, but I'm going to help you unpack the meaning that's hidden in here and how it's created. So, and yeah, they're bright, they're thoughtful, but we all have to get the deliberate practice, and it sounds like that's exactly what you're doing with your students, which is very exciting.
But the way you were talking seems so old-fashioned. Sorry.
Well, go ahead. Yeah, push on that.
Well, it was a great presentation, and it made me, think, well, what are these jobs we're talking about that people are going to go to, and what do you actually need for them? And
Yeah.
I'm pretty sure you don't need to integrate by yourself in 3 dimensions, no matter what it is, honestly. There's very few things where you need that. And why do we have these things called biology and chemistry and physics?
Yeah, I'm trying.
which
I
are not
have a
even
convergence slide.
those are made up things to begin with. So why aren't we actually really changing STEM education and not even having those things and discussing, what math you actually need, rather than, now that we have computers, rather than having these very, very old-fashioned ideas about, even for physics, what mathematics you need.
Yeah. No,
So-
I
And these secrets you're talking about for each, biology secrets, it sounds like certainly there are secrets, but I don't think they're biology secrets. I'm sure unpacking meaning, as old Peter was saying, is something we could do across STEM rather than having it in these silos.
We're trying, actually, so at my home institution at Carleton, we have funding from the Howard Hughes Medical Institute, really trying hard to press on that. And I think you mentioned physics for life science, right? You've been involved in that, and the really good work that Joe Reddish and Todd Cook have been doing, amongst many.
Actually, we're doing better work.
Well, I'm not going to get engaged in that. I think we'd
I
said.
know you work for the NSF, but okay.
Well, that's actually Howard Hughes Medical Institute money, so we're good there. But so yes, that's all true, right? So I actually have this convergence slide because I think that is a key issue. We also are. Do you think at Harvard you're going to suddenly get rid of all your departments tomorrow?
I wish we, especially our department.
do have too many of them.
Well, we are slowly getting rid of
Figuring
our-
out how to get there, yeah. We know, your point is so well taken. We know little about a lot of things within a discipline. The literature and the understanding of what it takes across disciplines to think about learning in a world of convergence is in the very early stages. I agree. I mean, I would not have put this together if I didn't think it was incredibly important. So I completely agree with you. I would love to hear how we get to that. It looks like someone over here also maybe had a suggestion.
Oh, no, I didn't have a suggestion. I had a question.
Because questions are important. I got it.
Yes.
I'm with you.
You started off with a presentation on percentages of people going to college, the higher SES and the lower SES. But I didn't hear anything in the rest of your presentation that showed how to address this problem in particular. And it goes back before college, it goes back to pre-college, in fact, starting from infancy, so to say. Does the NSF have any new ideas that might be useful in this area or not?
So we actually have, I think, some promising things. I intentionally framed this talk to point out where we have huge gaps in the research at the undergrad level because we don't disaggregate the data. We don't do the longitudinal studies. We're starting to do that. But I'm glad that you caught the dissonance because I structured the discourse so that it would really hit people that here we have this really important problem. Here's what we know. The one linker is that for all students, when you use these more effective practices, all students are more successful, but they're particularly important for students that come from groups that are traditionally underrepresented in STEM. So right now, probably the very best thing we could do for those students is to bring the more effective practices. We have a range of investments in a program that was called the STEM Talent Expansion Program that's now part of a broader program that went on for over a decade with figuring out what the different pieces were that would fit together to increase the number of students that graduate. And we have, it's a scholarship program, but it's got other pieces to it. I was talking with the research fellows today that I think it would really fit with some of the questions you're doing, our revised version. So we have, our evaluation is about to be released publicly, but we have a many-fold increase in the success of students that are in the programs that we fund in completing STEM degrees that come from low-income families. So it's a program specifically for low-income families. And it turns out that you need at least 3 or 4 different kinds of supports, and I don't think that the research is solid enough yet to figure out which ones of those are really the most key or where the synergies are. But it turns out a lot of these co-curricular supports are essential. So no matter how wonderful each of us is in the classroom, when we go in, we can't do it alone. So things like peer mentoring, the importance of math skills centers that people shape these in different ways, writing supports, and certainly the financial aid, so students aren't working. We have a neat experiment going in Madison right now. Sarah Robb Goldrick does really, really nice work. But a private foundation gave additional money to up the scholarships for half the students. They're paired, right? So that some have the standard amount of scholarship, which we can do, and we can't exceed that because of the way the legislation for our work is written. And then others have a bump up. And the idea is that students are more likely to persist if they want to be STEM majors in a STEM field if they aren't having to go out and get extra jobs and employment. So there's some really basic things like that. So it's a system, and it's a systems approach. Our institutional transformation grants are pushing on that. And which way works? There may be multiple ways. University of Washington and Washington State are using our funds, and GE and Intel wants to do a 5-year redshirt model using the sports analogy. So bringing in students that have come, primarily from under-resourced schools, they're all Pell eligible, and doing a year before in a non-remedial way, which is interesting to see how they're going to pull this off. But so far it looks promising, non-remedial way to get them ready, so they're not going in and taking Calc 1 with the students that took BC Calc and got a 5, but they're taking it again just to be sure they're going to be okay, right? It's not a level playing field. Cal State Monterey Bay and Hartnell College, a 2-year school, have partnered to do a 3-year computer science degree, 1.5 years at each institution. Their theory of action is that even with scholarship funding, low-income students can't last the 4 or the 5 or the 6 or the 7 years that it takes to get a degree because there are so many expectations from whatever shape their family commitments are taking. So there are a large number of national experiments pushing on that issue right now, and it may be institutional context specific, right? So we have everything going from community colleges to comprehensives to large state systems, and trying to make sense of that. And we do programmatic evaluation across the programs to see if we can find common themes. They're not easy problems.
What role are you seeing for undergraduates themselves to be engaging in research about undergraduate education? A lot of the discourse, both in the presentation, I think also sort of seems to focus on we're instructors and we're going to, think about these research questions. But, are you seeing, for example, REUs
Yes.
that are actually about undergraduates designing sort of educational research that they then are able to do, or outside the REU space? Is this something that you're seeing sort of an active involvement? Is there interest
Yes.
amongst undergraduate bodies for this? How would you sort of characterize that type of engagement?
Last 5 years, a real sea change. And I think it's really important because how on earth would you suddenly, you're partway through graduate school and you get interested in this? How do you build this kind of trajectory? So yes, we've seen not even a significant increase. We've gone from 0 to multiple REU sites that focus on STEM, education, research, and pulling undergraduates in REU supplements. We're seeing more like career awards in STEM education research where they integrate the undergrads as well as the graduate students in there. And I think it's exciting. And I'm hopeful. Again, I think data matters more than anecdote, but a student that was in my lab, probably one of the top students at Carleton, I don't think she had like a 3.9 something when she graduated, worked at NIH for a few years, and then did her PhD at UCSF and was phenomenally successful, has gone, and she's an instructional designer and for medical colleges now. And she she did most of the work on some really, really interesting laboratories we implemented at Carleton and kept testing it, working back with the students, being involved in the lab. I think one has to be careful in those situations, which certainly REU sites are, and all about student privacy, which you would be in any case, right? But if you're a classmate, you have to be really thoughtful about how you make sure none of that data is identifiable. We have a science education resource center that does large-scale national research, and when we use it locally, it's their staff that mask all the data, and there are a lot of serious conversations about whether any of it's identifiable, which that I think is the major risk. Does that help?
It does, yeah, thanks.
So think about an REU site award. Go for it.
You said a lot about math education, and I wonder if today the role that math has sort of played in creating students who think logically and coherently within a formal system could be replaced or augmented with computation. I didn't hear much about computation, and it seems that one of the reasons I've often heard for why do we teach geometry in high school is, well, in geometry students learn to do proofs and make sort of abstract arguments. And boy, if you learn to program a computer, you learn that you have to follow these rules, and the computer doesn't work if you don't program it properly. And I just wonder if computation has been considered here, and I didn't see any of that.
Absolutely. So I can tell you a little bit about that. I have several computer science program officers in my division, but I think the interesting thing you were talking about geometry. So in K-12, there's very little space in the curriculum for computing, and that is a huge issue. Jan Cuny has played a key role, I think, in pushing the development, both a 9th grade and a 12th grade computing course that's starting to get legs, and now thinking about how you move that into the undergraduate years. And we're going from not having enough pressure on undergrad computer science courses to having students from every discipline wanting to take computer science, which my guess is you're probably feeling that also. And it's not just one, but 2 or 3 courses. And how do we begin to get that back in? How do we move that into the disciplines where appropriate? So a lot of attention, a lot of work. Most of the work is focused on how do we get more women back into computing versus, when I was a student, there was a greater percentage of my classmates that did that. Again, I was just looking at our computer science education portfolio, and there has been in the past decade a shift in the amount of research, but in terms of doing research on learning about computing in the undergraduate years, that's one of the fields that's in a much more nascent stage, and there's a huge amount of opportunity there. And really good, important arguments that you make, absolutely.
A quick note that we're coming up on 3:30. I know a number of people had to leave, but we do have the room for longer if people want to stay and continue a conversation.
I have a question about, so one of the things that's interesting about education research is that education is largely done by people who aren't education researchers, and there's this other group who are the education researchers, and we necessarily should have some sort of symbiotic relationship. But even if you're amenable to this, so we're not collaborating with somebody who I've known for a long time at Purdue, who's an actual genuine card carrying. She has a card that says she's an education researcher, which is very handy. But and we're submitting NSF grants together, and I'm pretty sure I'm a liability on those grants because I have no background in education research, even though I'm somebody who's trying.
You might be surprised. My crowd still really gets it. We have, the language is probably not particularly helpful, but there's education researchers and there's scientists, and because of the way I think this division grew up, they really, really like to see the scientists in the mix.
I hope that's true when it gets reviewed. But but how do you encourage that kind of, because it's great. She just won a career award, so she has tons of resources to be sort of studying what we do, and then meanwhile we're sort of starving to have anyone on our end to interface with her when we're developing these things. So
why don't you see if she can get a supplement or a career award to bring you in more fully?
We may do that. I didn't know that was possible.
You can get up to 20% of the value of the award, yeah.
But in any event, I mean, are there programs to encourage specifically this sort of the other side, and what should we be looking at, and what should we be thinking about in that regard?
So there's a program, we call it our Education and Human Resources Core Research Program, and it integrated it was called REAL. I'm sorry, the government is just full of acronyms, and I'm going to just apologize in advance. But within that program, there has been a long-standing effort. It was called FIRE, but basically it was a program where you could bring together you and your colleague at Purdue to work together. And the odds of getting funding when you come together with that combination asked to do it are high, because we are trying so hard to push partnerships. And the National Academy of Education, the National Academy of Sciences have been thinking really hard, and it's not all the way there yet, but could we create a postdoctoral program that would bring together, and they are even not just practitioners, but the Deber scholars, get them together with someone with social science expertise. So we are very interested in using our levers to find ways that people can work together long enough, which maybe with your physics and life science you're also finding. I mean, you've got to spend time together and realize that you're talking past each other before you develop a common language. So it's really a high priority.
So can I ask about the longitudinal studies? You said they aren't being done.
They're getting there, but
How long should a longitudinal study be? Do you have a thought about that?
I probably have at least one thought. It seems to me, and again, this is based on work that comments from a broad community and also our personal work with following the effect of a new problem-based intro bio class. You got to follow the students through graduation, right? So you want to see what happens at least as they move through the undergraduate years. It gets really tough to track people beyond. We have all sorts of pilots going with REUs, with our cybersecurity grants to do it.
Tracking, because if you're teaching them, let's just say, how to think in a certain discipline, and then they go off and become convergent. Right now, I don't believe we know how to teach people how to think in two different disciplines at once.
Don't.
But we can do it in one discipline, and I think it's actually incredibly important to be able to think in one discipline and then be able to reach out.
Yep.
What happens if they're trained as a chemist or they're trained as a biologist, and then they end up in biochemistry or medical?
So probably biochemistry we know more about, because that's actually, like with convergence, you go from divergence to convergence in the extreme. It's like biophysicists are now a discipline, or biochemists have their own discipline, although they argue over who belongs in chemistry and who belongs in biology, and they have a different flavor based on that, right? It's really complicated. These are very important questions to ask, and I don't know that we have the methodology in place, or people have pushed hard enough on it. But I mean, that's why I was excited. I took the time to pull up the convergence slide, because I think, you think about the next frontier, we've got to figure out how you get the deep disciplinary knowledge and how you're fluent. I mean, I keep talking about convergence Creole, because you need to be talk across the disciplines. So
I'm just wondering.
But those are two different questions, right?
That's correct. Having done a number of conferences at the National Academies where we are forcing convergence.
Right.
That is to say, people who have been in particular disciplines, then forced to work together and to understand each other for a long enough time that they actually realize that these things that are secrets are actually
can be
concepts,
made visible,
and they
right?
can be made visible, and they can actually talk to them, and that actually there is science there. I mean, I'm talking as a physicist. Physicists will know what I mean. And it turns out, at least in my anecdotal observation, that the younger people are much easier and more fluent at this than the people who, say, are in their 50s. And so the question that I have is, let's just take a biologist and a physicist, or and get them thinking critically in their field as an undergraduate, and then have them work together in the same lab
So you
as
know where
a
you could
graduate student, or have them continue in their field until they become a professor.
So you could use the, they're called National Research Traineeships. So it's a cohort model, but there's also a research track there that's new. And we're trying to get people to think about how we can begin to ask really innovative questions in that area. You could set...
So my question is it better in graduate school, or is it better to wait until you're a postdoc? Or is it better to wait until you are at the professor level? How much depth do you need in a field to be an expert is, I guess, the question.
Sounds like a really great research
And it's not,
question.
as you're thinking about, how do you train people in convergence, I really, really worry that if you start at the undergraduate level, you're losing a huge amount of depth in a field.
So that's talking about going to an interdisciplinary degree, right? Like, so environmental studies is one of those. Yes, my child, we insisted she do the geoscience degree also, and then she could do environmental studies. I think that's really different than being a physicist, but having a learning experience where you are bridging fields and you're learning to talk
that's
with.
different. That's like a secondary field as opposed to this completely interdisciplinary.
Right, right.
Are you funding studies on
Well,
what works
by-
best? Or
so what's interesting to me, we saw a huge shift. It was always the engineering proposals that were the big bolus that came in. And this year, it shifted to things that we would characterize as interdisciplinary.
Yeah.
But many of them are not pushing on the questions you're asking. They're just assuming if we bring together different groups, this will happen. Now, just because people submit proposals doesn't mean they get funded, right?
Right.
And I would say that's not a particularly
that's not-
inspiring
yeah.
way to go. I think the longest term example we have as a country is what happens at Evergreen College, where from day one, everything is taught in a very interdisciplinary way, where a physicist, a chemist,
Right,
a biologist are teaching together. And I guess I would just observe that has not scaled. They're tough questions, and quality matters.
Can I ask a follow-up question about the longitudinal part of the question?
Sure.
Which is maybe to have you kind of characterize what you have seen the barriers being to those types of studies. Some of them are certainly going to be on the privacy and the sort of things that like makes Aaron's head spin sometimes. But then also, are there instances of sort of collaborations with industry? Because if we're thinking about sort of real longitudinal type things, it's all right. So, and I was struck by the sort of New York Times article that was like Goldman Sachs says that like this set of things makes them successful in their organization, and Google is just like the complete opposite.
Yeah,
right?
we
And
talked to so many different industry folks, and they're just.
like that.
And you talk to the CEO, and then you talk to human resources, and they're not on the same page in the same company.
But that's the flavor. I don't know. I just want to get at that. What are the obstacles to doing real longitudinal work beyond the obvious privacy things, and then
And the funding, right? Because
and
we
funding.
cannot fund more than 5 years.
And then what is?
But you can get another grant.
Yeah, and then what is the role of industry in any of that?
So that's a conversation I've been having, as we're doing a lot of planning conversations and everything. Are there ways that, at least from the federal perspective, we can work more closely with industry, or even, you think about retention of women. We could make everything wonderful in the undergrad years, and if we're not changing the work environment in, say, engineering, the gains are more limited, right? And figuring out how you partner there is really, really tricky, because again, the privacy things, but also the motivation for industry. So where we've actually seen the most success has actually been at the community college level. For 21 years, we've funded a program called Advanced Technological Education to prepare technicians, in biotech and advanced manufacturing, photonics. And to get an award, you have to have a robust partnership with industry to start with. And the very strong ones that have gone to be national centers, they have quarterly conversations with the industry, with aligning the curriculum with the industry needs, and back and forth. And there are student internships that are built in where the industry provides the internships, not the full registered apprenticeship model or anything, but the internships. So there's really good alignment, and there's learning that goes both ways. Where that gets harder, again, at the 4-year level, that's part of this 4-year, it's called STEM Scholarships for STEM program, also there. It works when you have regional workforce issues, and the graduates are more likely to stay there. Now, I know Senator Markey has said several times that in Massachusetts, you get them here and then they stay. He released my child, I thought, but she's now back in Boston, so maybe he's right. She graduated from Mount Holyoke. But if they're going to work in the region, it gets much more complicated nationally. So right now we have a very interesting investment at, at the 4-year level. Business Higher Ed Forum is leading it, but you've got regional pairs of university industry partners. So in St. Louis, it's Boeing and WashU. With cybersecurity, it's the University of Maryland and Grumman, Northrop Grumman. And so what they're trying to learn in the time that we funded them is how they work on the alignment issue and how students move in that space. So we can work kind of at that interface, but that doesn't, none of these fully answer all of your longer term.
I mean, I guess what I was trying to get with the longitudinal bit was
Thanks for coming.
Any
Very nice to meet
efforts
you.
to align research interventions that are done at the university level to success in industry, right? So, half the intro physics class at Maryland gets one thing, half doesn't, and then Grumman actually tells you, we're not just looking at tests within the university, but
Right.
we're getting Grumman to give us feedback on later on.
Yeah.
Is that?
That's very possible. In fact, I just did a site visit at Hudson Valley Community College in upstate New York where they prepare, it's a nanotech program. Students that go into Global Foundries, which is the largest semiconductor fab in the world that happens to be in Malta, New York, right? It's Abu Dhabi funding that goes into it. So it's a very different kind of infrastructure. And they did two things. One, they pushed back and said, you've changed your program to make it more theoretical, and these students are no longer hitting the road running. So either you fix it or we're not hiring them. But then they also came and said, we hired all these 4-year engineers from institutions X, Y, and Z, and it's a disaster on the floor. So could you please come and do training? So now they're doing the training for the 4-year institute. But because things change so fast in certain industries, how do you build that continual feedback loop? Because again, that example was great. It worked for Hudson Valley beautifully for a decade, and then they thought they were doing something great, and oops, it didn't work, right? The students weren't getting jobs.